Thank you. Right. Starting with a quick introduction, then go to the methodology for contributions, some results, and then roadmap for research work. I plan to start the presentations with this slide to set the tone for the rest of the presentation, because some of the mining applications have been gaining some negative momentum nonetheless than the previous few years, just because we're looking at decarbonization and it's etc. We're all for it. We're all contributing to the best of our knowledge, but also I will stop looking to mining when we basically have all the critical minerals that we need for the green transition. And until then, we actually need to do it in the most sustainable and efficient way that we can, and we can optimize for. So mining complexes are basically large-scale industrial systems where we manage the extraction of material from the ground, but also every single operation that happens within the mining complex, or that can be integrated within the mining operations, and that includes the drilling, the blasting, extraction, hauling, processing, etc. So from the mines, including downstream, up until either the customers and or to the spot market. And by including all of these steps or processes in one single mathematical formulation, we're providing a simultaneous optimization of the mining complex, but also in a stochastic way by integrating the uncertainties that might occur, either internally within the system, but also externally. Think about the price of commodities, for example, also conditions that the mine planner does not have any control of. So by simultaneously optimizing the mathematical formulation, we have multiple sources of complexity. The first one is clearly the sense. We're not looking to 10 or 50,000 blocks, we're looking to millions, tens of millions of them. And that results in a mathematical formulation that contains tens of millions of decision variables, constraints. We're looking to non-linearities, both in the objective function and in the constraints. Think about the blending requirement. Think about losing the predictability or the traceability of the blocks once you extract them and actually send them to the stockpile. But we also have too many sources of non-linearities that we want to keep information as truthful, what is actually happening in the real life, what is operated by the mine planner as close as possible without losing some of that in the smoothing processes, etc. We are optimizing the formation simultaneously, as I was saying. So the extraction, when are we extracting the blocks, the ore body mining blocks, if any, meaning basically if we're extracting them, and if yes, at which period, at which year, from year 1 up to life of the mine, let's say year 20 or 25, the destination, where are we sending them from the mine to the first destination out of the mine, meaning are we sending them to the waste, stockpile, processing plant, etc., etc. And then the processing scheme for downstream, which is a continuous flow of the material. So once we go out of the mine, we don't talk about discretized 3D already blocks, but we talk about the material that is being sent from this destination to the next one, etc. But we also integrate in the capital expenditures. Think about electrification, think about the number of trucks, think about repositioning some of these material plants, etc., and operating modes that happens or that occur and that actually can decide and change the uncertainty set or the simulations that we're using. And finally, we have multiple sources of uncertainty. So we have uncertainty mainly from supply and demand. Supply means that we have limited knowledge about what might be in the ground. As simple as that. If we have perfect knowledge and perfect sensory information that we can use to exactly know where the nuggets of gold are within the ground, then that would be perfect information, but we don't have that. We have only limited information from doing some drill holes and extracting a limited sample of what might be in the ground, and we use them to estimate, to have some approximation of what might happen in between these drill holes. And we have limitations on the number of drill holes because they're expensive, but also because we cannot just drill hole the whole ore body mine. And also uncertainty in the demand, meaning that the price of the copper or the gold or the price of the critical minerals or even the demand for lithium will be increasing or decreasing depending on external factors from the mining company. And we need to integrate that within the mathematical formulation and account for it in our stochastic formulation. And the reason for accounting or the rationale behind accounting for it, just think, for example, what happened in the pandemic, where between a month and the next month, the price of the copper and the gold just skyrocketed just because there is an increasing demand for it, and that is how the market goes. So we actually need to integrate this somehow in the formulation to account for these uncertainties or these scenarios in order to proactively prepare for them and manage the risk in a proactive way before that even happens. But we also have other sources of uncertainties, equipment performance, operational costs, etc. And the more scenarios or the more sources of uncertainty we include, the more complex the mathematical formulation becomes. Think about if you are solving for 3 mines, you have 10, 20 simulations for the first, 20 simulations for the second, 20 for the third. Well, the set of scenarios is 20 times 20 times 20. And so it increases really fast with the number of mines or the number of sources of uncertainty. And so for a quick example here, which is not even a large scale example, if you're considering 3 mines with, you can easily find 9,000 joint scenarios, and you can end up with 20 million decision variables with around 60,000 continuous or 500,000 continuous variables that we need to account for, with tens of millions of decision variables. And this is, again, not even the largest case study that we can look into or optimize, with only in total around 700,000 nodes. So what we're presenting today is a solution methodology to optimize faster, better. That is what we're doing. That is what we're looking for. Just a solution methodology to account and to solve as fast as possible, but also provide the best solution that you can find in a reasonable amount of time, meaning if you're optimizing for a mining complex, you can wait for days, weeks, but you cannot wait for months or years, because we do this in a quarterly manner or fashion. So for the solution, I'm going to provide or present our diving, branching, some theoretical analysis about the both of them, and then some distributional one starting. And application are a large-scale mining complexes with up to 20 million variables optimized in hours out of weeks, with some uncertainty quantification about the price. Why do we even care of including the prices in the first? Because the literature has been again and again showing that it is important to include the geological uncertainty, but it has not been as determined or deterministic or final on including the prices in the first place. But the question is, do we even care? Make the mathematical formulation even more. So we use a two-stage stochastic integral programming model where we take some of the decisions, namely extracting the blocks, etc., etc., and then we look into what is the realization, what is the actual reality that happened, what are the quality of or degrees of the blocks that we just extracted, and then we send them downstream. And so we do this in a two-stage SIP, standard one. For the uncertainty that we incorporate, as I was saying, uncertainty in the supply, uncertainty in the demand. For uncertainty in the supply, what we do is that we discretize the ore body model into 3-dimensional blocks characterized by a set of simulated attributes, grades, material types, etc., etc. And then we use your statistically simulated scenarios of the mineral deposit attributes that we generate or we develop, either using second-order, think about sequential Gaussian simulations, or high-order simulation frameworks. For the demand, for the price, it depends on what is the material that we are looking into, or the mineral that we're looking into. For the base metals, we use a mean reverting process with a Poisson jump diffusion model. For the precious, as in the gold and the second study that we're going to show today, we use a tandem geometric motion model with Poisson jump diffusion. We can do more by looking into multi-stage adaptive SIP by updating these scenarios. But the first step to include the price uncertainty into the formulation is to use what is very standard and agreed upon in the literature to model the uncertainty around the base metals and the precious metals. And these are the two closed from stochastic models to generate these simulations. So now, in order to solve them, where do we look? We look into the literature. And basically, there are two ways to include machine learning and efficiency research or optimization in the literature. The first one is to use machine learning augmented optimization, where machine learning comes and provides some guidance in order to accelerate the optimization, meaning the machine learning is feeding knowledge in a way to the optimization. The second one is to end-to-end optimization learning, where machine learning is combined to generate the solution directly, the whole solution, and not just nuggets of information or parts of knowledge or information. For augmenting the optimization, you can look into it as continuous optimization or combinatorial optimization, learning to branch on CAD, heuristics, etc. Or end-to-end is to predict solutions either with constraints or learning on task. So what we've been doing during this work is basically to look into the methods under these two paradigms, under these four directions of research: learning heuristics, as in providing a meta hyper-heuristic with a certain set of perturbations, how to perturb the current solution in order to improve it in the best way and in the fastest way possible. Looking into learning to branch and literature to provide some guidance, some robustness, some guarantees on top of it, but also using neural networks and learning with constraints to provide knowledge to the optimization, but in a reasonable way where we integrate as much as possible the constraints into the learning phase to increase the feasibility, right? It is still the meta and hyper-heuristics that do the work for us at the end of the day, but we provide knowledge as much as possible, and I will provide more details as we go. So for the solution methodology, we basically have four components in that. The problem domain, the simulated annealing, to either accept or reject a certain perturbation at every iteration, norm diving, and norm branching. And I'm going to go on each of them now. For the problem domain, it contains all the information that we need to encode about what problem are we optimizing. And that means that if you want to generalize or use a solution methodology on any other problem, this is the part that you need to change. That's all. All of the other components are transferable and calling the problem domain. So the problem domain contains the evaluation function to basically, given the current solution, can you give me its objective function value of this certain iteration? It contains a way to provide or to generate an initial solution, the problem representation, but also the set of neighborhoods that we're going to use. The set of neighborhoods, meaning that we have 30 perturbations divided into 3 neighborhoods, and each set of perturbation provides or perturbs a certain subset of decision variables. We have a first neighborhood block extraction sequence perturbation that will go to a certain block and change, advance or delay its extraction period. We have the destination policy that says we take this cluster of blocks, and instead of sending them to this destination, we now send them to another destination. And we have the processing stream perturbation that takes a certain continuous flow downstream and provides a certain perturbation using Gaussian process, basically, to some Gaussian norms to change the quantity of material that we send from this destination to the next one. So at the end of the day, these are low-level heuristics, perturbations, just to move from the current incumbent solution to the next one by doing a small change, right? Some of them are take a certain block. Some of them is remove the whole branch, the whole level of blocks. Some of them are take a small cluster. Some of them are more aggressive or major. We use simulated annealing to iterate between providing or making a certain perturbation to the current solution and then deciding whether to accept it or not. The acceptance criteria is depending on the change in the objective function value, but also the time that it took to make that heuristic, meaning that maybe we will prioritize making small perturbations that are quick instead of having another one that takes, let's say, 20, 30 times the time, but makes 2 times the difference of the objective function value or the improvement of the objective function value. For the next of the methodology, I'm going to focus on our diving and branching. All right, so for now, up to now, what I've been showing is a typical hyper-heuristic framework that is used to basically solve as quick as possible. In the meantime, there is a way to include or to augment this hyper-heuristic with machine learning and or reinforcement learning in 2 ways, neural diving and branching. So neural diving is basically computing a confidence method for each of the heuristics to try to predict what that heuristic would do if we choose it for the next perturbation or the next n perturbations. What is the estimated performance of each of our heuristics? And we have a confidence method that we're going to use. And for neural branching, what it does is it basically focuses or augments the knowledge of the hyper-heuristic to focus on certain regions of the orbody model, meaning we focus on a certain set of variables for the next n iterations. If we look into branch and bound or branch and cut, what does it mean? Variable selection, we just provide a machine learning, imitation learning to decide which variables we're going to branch on next for the next 10 levels of the tree, but we do it not in an imitation learning way, from a reinforcement learning proactive way. All of what I'm presenting here is a zero-shot learning, online learning, meaning there is no pre-training whatsoever, to be clear. Now, neural diving, basically the intuition is the traditional machine learning heuristic selection way is at each iteration to select a single heuristic, apply that heuristic, and then to accept or reject using the simulated annealing acceptance criteria. So select, evaluate, then accept, then go again. What you're providing or what you're proposing is that you compute a confidence method. We apply a certain adaptive neighborhood selection, which I'm going to present in more detail later. And then we use that adaptive neighborhood selection to dive into a heuristic selection tree, the primal heuristic selection tree. Diving, meaning we jump some certain number of levels without evaluating at every level. And I'm going to provide more details. So the traditional way is we select a certain heuristic, we expand, and then we evaluate. Then we look into the next level of the tree, we select a certain heuristic, we expand, and then we evaluate it again. So the traditional way is to evaluate every level and basically select at every level of the heuristic selection tree. What you're proposing here is that we do not evaluate as every certain level of the heuristic selection tree, and only when needed using this confidence method. So for the pseudocode or the algorithm, what we do is at each step, at each iteration, we compute a confidence method based on every single heuristic, let's say 30 heuristics that we have. Some are minor, some are aggressive, on what is the estimated future performance of these heuristics. Then we define an adaptive neighborhood based on the estimated performance. We provide a depth first search in the heuristic selection tree, the primal one. And then we apply this neighborhood that we just constructed. We basically zoom in on a certain neighborhood, and then we jump a certain level. We aggregate the heuristics that we're going to perform, and then only evaluate when needed. And what that means is that we adapt the size of the neighborhood depending on how confident we are on the estimated future performance of the heuristics. And once we provide or we perform these sets of heuristics, aggregated heuristics, we update the state, we compute the reward, and update the parameters. So every iteration, instead of evaluating at every single level of the tree, what we do is that we aggregate multiple of these heuristics, and then we expand and evaluate only when needed. So we only evaluate at the, for example, root node at 0, and then only after 3 heuristics, depending on how confident we are on the actions or on the future performance of these heuristics. And we do that because it takes a long time to evaluate this value chain. It takes a long time to evaluate tens of millions of decision variables and making sure that all of the constraints are satisfied and providing the final feasibility restoration process. The evaluation is what takes time. It is not the performance of the heuristics. It is not the expanding. It's the evaluation of every single one of the decision variables. And that is why we only do it when needed and not at every single step. We provide some results in the visual paper. Some of them are to prove that the diving depth is directly proportional to the agent's action. And I will leave it at that for now. Now, going to the neural branching. Basically, the state of the art in mining, but not only in mining, is to flip a coin and to choose blocks randomly and basically put all the pressure on the heuristics. And that will make sure that we only choose the heuristics that are safer. But that also means that we are going to provide or prepare the solution in smaller manner, meaning that if there are blocks that are really high quality at the bottom of the pit, it will take a long time to reach them because the optimizer is risk-aware in a way. It basically tries to flip a coin and choose blocks randomly, which blocks to perturb next, which variable to perturb next, and then it does that in a very incremental way. Instead of doing that, what we're providing is basically to learn a block or body block, sampling function to branch on the promising blocks, to branch on the promising variables. So, learning to branch just in an actual industrial large-scale stochastic setting. We define a hypergraph where the nodes that you can see in here are literally order blocks. And then the arcs that you see in here provide the precedence constraints for basically the sort constraints, safety. And then we want to decide which blocks are having a high versus low likelihood to be selected for the next n iterations. Which blocks do we want to focus on for the next n perturbations, for the next 100 perturbations, which region of the ore body mine we want to perturb that would increase the objective function value in the fastest time possible. And the nodes are characterized by static features and dynamic ones. And for dynamic, we have features that are appropriate or coming from the solution vector, but also ones that are contextual features that we incorporate them here, including the price. We define the sampling function that gives the probability of selecting each one of the already blocks in the mine, given a certain parameter vector theta prime. And then we define a mapping function that provides the probability of selecting each of these blocks under this set of vectors. So what we do is that at every single iteration, we iterate between updating the sampling function for the blocks. We use the sampling function to determine which blocks are to be fixed versus unfixed. And what that means is if we determine that a certain set of blocks is to be fixed, that means that it will not be changed for the next 100 iterations unless we need to change it to restore the primal feasibility of our solution. And that means that if a certain block is to be fixed, we will not perturb it unless it's to restore the final feasibility of the solution. Once we determine the blocks, we generate the next incumbent solution by providing or by aggregating the heuristics as I was saying, as I was showing in the neural diving, restricted on the unfixed blocks that we just defined. And then if it is accepted, we compute the reward function, the parameters, and then we update the hyper-graph. We provide a couple of few architectures to encode this set of features, all parameterized by the set of weights that are prime, and we provide 3 ways in the paper. The first one is to use neural networks, the standard neural networks. The second one is to use graph neural networks. that will take into account the structure, the spatial structure of the problem, to provide a sampling distribution in one shot instead of providing block-based sampling probabilities. And the third one is to use convolutional neural networks. And we provide a few terms out of it. The first one is that the expected quality of the solutions that the neural branching agent will output will either improve or remain the same with each successive iteration. That means that in the worst case scenario, the neural branching will not get worsened by iterating with the optimizer. The results will only get better as the learning agent is improving its results and selecting which variables to branch on next for the next n iterations. For a small change in the parameters of an optimal policy, the change in the objective function value is also small. And that is also important because imagine if you change the grade of a block by 1%, and it clearly and completely changes your solution or your policy, or it takes now 2 weeks to re-optimize the solution. And that is something that you do not want. You want the solution to be robust, but you also want the optimization process to be robust as possible. So we show that for small change in the parameters, the change in the function value is also small, and that assuming an appropriate tuning of the reinforcement learning rates, and we clearly provide how to do that, the neural branching algorithm will converge to a policy. So we do show the convergence, not of the overall hyper-heuristic or algorithm, but of the neural branching agent. And that under a broad class of non-stationary environments, conditions, referring back to the contextual features that I was mentioning a few slides before, the neural branching agent that we are providing, that we are optimizing over, is more robust and adaptive than any other agent that you can use for sampling the blocks. And that means that if you come with any way to define the sampling function, we show that the block sampling function that we provide here is better, maybe not in one environment, but as soon as you change the mining complex, if you look under a broad class of these environmental conditions, by changing some of these context features, the neural branching agent that we provide is more robust and adaptive, meaning that maybe what you just defined is better, but if the price will change, if the solution will change, if any of the contextual features will change, then our agent will become better. And the last piece of the puzzle for the optimization, for the methodological contribution at least, is to provide the warm starting procedure. So I'm going to start with standard, typical, imitation learning way, and then move a bit more complex from that. So we start by providing a data-driven warm starting procedure to basically not start from unmined. Every block is just unmined. Just provide a better way to warm start. And there have been a few attempts in the literature, but again, not generalizable enough. If you provide a certain way to initialize, it heavily depends on how you define and the actual intrinsic characteristics of what might happen or what is under the ground. And so we try to provide a generalistic way as much as possible to warm start. All right. We store the past solutions from various other different mining complexes. We decompose this problem into a learnable local problem per or body block that we know to be in here, okay? And then we ask one simple question, which is whether that block is within the same extraction period as the block above it or not. That's all. Meaning, we try to predict the connectivity of the edges between two blocks. That is all, a locally learnable problem. Then we train using an imitation-based decision maker. So we start with a pool of solutions, we decompose the problem, we use a flow problem that I'm going to show later, and then what ends up out of this process, what we output is an initial production schedule an extraction sequence that we will input into the optimizer, the hyper-heuristic optimizer for hyperdimensional. So we end up with a production schedule, and that is it. Not the downstream, not the destination policy. All right. Now for the capacities, what we basically do for the capacities, or what we want, is to make sure that we don't exceed the mining capacities of the mine per period within a certain range. And that is what we're doing here by providing the capacities within the arcs and providing it within a certain range defined by M here that we tune to the mining complex. So typically 100%, but we might go a bit above to provide some leniency that we need to observe later on. So we store the past solutions, decompose the problem, then what we do is we take all of these probabilities for block, and we basically solve a mean cost max flow problem. As simple as that. So this has been done many, many times in literature. This is not new. Maybe in mining it's new, but we have been seeing it in the last couple of years in other contexts. Now, a bit more complex, only for a couple of slides. What we do is that, all right, instead of looking into the top one, which is what we typically do in machine learning for settings, the top one connectivity between two blocks, what we can do is that we can look into the top K. Instead of having the connectivity between a certain block and the one above it, we will also look into, well, what do you think is the most reasonable scenario or setting choice? But also, even if that doesn't happen, look into the other options, look into the second, third option, and then what are the probabilities for those? And we can encode them in a frequentist like reasoning approach, rationale, or an information theoretical approach. Then what we do is that we use a graphical model to encode all of this, where V represents the mining blocks, the nodes that I've been showing, E represents the precedence and the spatial relationships, and P encodes the distribution of the historical block connectivities. So what we're doing is not providing the candidate, the top one candidate, or even the top K candidate. What we're providing is the full distribution of probabilities that we input from a certain machine learning model. And we do more by providing multiple machine learning models and providing multiple votes, but also by sampling the price scenarios. So what we end up with is a distribution P that encodes what are the votes from multiple machine learning models, as many as you can and as you want, but also from looking to what are the possible scenarios that might happen if you change the price by 0.5%, 1%, etc., etc., etc. And we encode all of that into the P set of distributions here. And use all of that to provide two sets of solutions, or two kinds of solutions. One that depends on the distribution from the set of from the ambiguity set, and one that is risk aware. Without going too much into the details, what that means is that we take all of the votes in, and then we try to incorporate that into the flow problem, right? So we just change the objective function. The set of constraints is literally the same. And we use a certain distance measure. Think about it as a certain cost function to go from P to PM, which is an empirical distribution from the historical probabilities that we just provided. It's a mass to move from P to a certain P empirical. And we use all that to provide a distributional warm starting, meaning by using distributional robust optimization to take all the probabilities in and to provide one single risk-aware optimal solution. Here is the worst case. And that means that we provide a certain warm starting solution that takes all of the votes into account, and not only the average of the votes or the P1090 of the votes, etc., etc. And what we get from that is not only multiple solutions that now we can try quickly, because we don't need to wait for a lot of iterations. We don't need to re-optimize the production schedule. We only need to optimize the downstream, which is quick because it's continuous variable and continuous flow. But also we get a risk-aware optimal solution that we can directly inject as an initial prediction study onto the optimization. Plus, what we get from that is not global guarantees, but we do get statistical guarantees out of the distribution robust optimization. All right, now some experimental results. I will just show two mining complexes here, but the papers contain, well, one that is a smaller case, even if it's larger than what exists in most of the literature, copper mining complex with around 200,000 blocks and 2 million variables, and one gold body mine with 20 million decision variables. All right. We start with optimization progress for the copper mine, then the gold mine, then look into the solution, meaning, great, we're optimizing faster. Then what? Is the solution actually better? Do we gain in net present value? Do we gain in risk management? What do we get after optimizing faster? So let's start with the optimization progress. What we see for the copper mine is that the execution times are reduced by around 70 to 80%, comparing the baseline, which is the state of the art for optimizing mining complexes, and GNN and BND, which is basically neural diving using typical neural networks, but also neural branching using the graph neural networks as a set of machine learning model to incorporate the weights in them. So if we compare the baseline with the best variant there is, again, in an online, non-pre-trained fashion, we reduce by 70 to 80% the execution time and the number of iterations. When we look into the gold mine, at least for the beginning of the optimization, what we see is that we reduce by 2 orders of magnitude the execution time between the baseline and the GNN version. But we wanted to see what happens then. Maybe it gets stuck actually and the baseline becomes better. We don't know. And so we wanted to wait until the actual convergence to a suboptimal solution and to see what happens then. So when we wait for a longer time, as in days, what we see is not only are we optimizing faster and better, but also that any of the solutions from the baseline, the state of the art, at some point, it doesn't even get to the same solution because it is a conservative incremental approach. Because the neural branching is more risky, and that means that it tries the more aggressive perturbations as soon as possible by targeting the blocks that will improve the objective function value as soon as possible and as quick as possible, instead of the state of the art, which is basically incrementally providing the heuristics one after the other. Now, do we even care about including the price uncertainty in the set of scenarios? Do we even care about increasing the complexity? So if we look into the final solutions and compare them, what we get, at least if we look into the net present value, we can look into any of the KPIs or any of the results from the mining complex, but at least the minimum is to compare the net present values. What we see is that we improve the net present value over the life of the mine and the copper mine by 5%, and for the gold mine by 40%. Having in mind that this is a large scale, maybe not the largest scale case study that exists in the world, but probably around there, at least in the literature, in the academic literature, we improve the MPV by around 40%. Now, effect of commodity price uncertainty on the downstream. What we do is 3 simple experiments. We keep the geological uncertainty in all of the experiments. We don't touch it, right? It's all stochastic under geological uncertainty. The only question is, do we even care about including the price uncertainty or not? That is the only question that we're asking in these 3 experiments. And so what we do is provide deterministic 10 simulations, 100 simulations. Deterministic refers to the price uncertainty only, and then we look into the risk profile generated. But what we get, if we compare all 3 experiments, is that we get an improvement over the life of the mine of between 8 and 10%, and we get an improvement every single year for at least 1 or 1.5%. And what we can see in here, funnily enough, is that at year 1, incorporating the price uncertainty actually worsens the results, worsens the net present value. But keep in mind that we are optimizing the net present value over the left of the mine, right? Discounted cash flow, but we're optimizing the final value here. We're optimizing over all of the mine and not only the first year. Now, what did we see today? Machine learning augmented solver for stochastic optimization of mining complexes, presented normal diving, branching with some theoretical analysis, etc., with reduction in execution time and iterations by 3 orders of magnitude. Specifically, if we look into the gold mine deposit, the second case study, if we look into until the convergence to a suboptimal solution, we don't cut to the first warm starting or beginning of the optimization period. We decrease this primal suboptimality by a factor of 2,000, and we increase net present value by 40%. And a final quick experiment to see that actually increasing the percentages here in this case study provides a more favorable realistic risk profile to be continued. So for future work, there are 2 directions here. Short term, which is what will appear shortly, and then long term. For short term, what we provide is distributional robust work starting, as I was showing, but we can use it in multiple of interesting ways. Because now we don't only have an initial solution, we also have the connectivities between the blocks, right? So think about like a maximum flow as a name on cats, like you're literally providing cats, and a certain cat is a certain period of extraction of the blocks, like this is year 1, this is year 2, this is year 3, and you're clustering the blocks in this manner. But you also can use that to augment your neural branching agent to accelerate the learning, meaning now we don't need to provide or consider all of the connectivities of the blocks when you are sampling. You can use it in multiple interesting ways into your optimization, but also from a theoretical perspective, because you're getting statistical guarantees, but you're looking to provide more guarantees as much as possible while you have a reasonable execution time. Diverse solution generation to provide not only economically viable solutions, but ones that are environmentally sustainable, that account as much as possible, as much as you can from a long-term perspective, the sustainability, including or rather separating, making the distinction between what is indigenous and what is exogenous in the uncertainty. And that means that up to now, we basically considered all the uncertainties as exogenous, while actually if you're tuning the operating modes, that actually changes your throughput, that actually changes your uncertainty set. And we want to provide a risk-averse stochastic model that integrates these indigenous uncertainties from within the system itself. Not every uncertainty is exogenous of the system. And then decentralized decision-making, process for resilient supply chain. Longer term, we have 1 to 4 challenges. So basically what we want to do is to look into how to better model the uncertainty that is within, intrinsic to the problem that we're solving, but also external to the problem. How to model it, how to represent it, and how to quantify it. We want to solve faster, better. We're always looking into addressing more computational complex problems. We can include additional mines. We can include like bigger mines that exist, right? Hence, these 2 challenges are not that distinct or separate from each other as much as one might think. And then we want to improve the robustness and the resilience of the solutions that we provide, meaning we want to optimize faster, better, but also in a robust way for the optimization itself. We want for the optimization to be as generalizable as possible. And if we change a certain parameter of the solution, we don't need to completely fine-tune it, and we really need a deployable solution framework at the end of this, and not just some academic contributions that we will forget about. And some trustworthiness behind the solution that we provide, meaning some theoretical analysis as you've seen today, but also additional ones, and certificates, guarantees, bounds, and robust explanations as much as possible, and then applying them on transportation systems, sustainable supply value chains, but also for equivalent system solutions. Thank you. And these are the companies that support the Cosmo consortium. I think thank you.